All right, class, let's go ahead and get started. Today we're going to cover statistics. This will be something of a review primer if you've had a little bit of a review, if you've had a little bit of statistics before. If you haven't, this will be something of a primer for the 601 class to get you ready for the statistics you will do in that material. And I've also constructed some examples that will just help us think about how business students would look at statistics and use statistics. And there'll be some things that you can do right in class today using basic statistical information and stuff you probably already know a little bit about. How you doing? Come on. So we're going to start right off with some basics, what statisticians call measures of central tendency. If you have a bunch of data, how might you analyze that data? Well, there are three measures of central tendency you can use. They are the mean, median, and mode. The mean, does anyone know what that is?
The average?
Yeah, it is the average. The median, does anyone know what that is?
The middle number.
Yes, if you were to line up all the numbers in the entire data set, the median would be the one in the middle. And the mode?
The most recurring number.
Most recurring number. So the most frequent number. If you were to put all that data in a frequency diagram, or frequency plot, frequency chart, like we will do later in class, it would be the most common number, the one with the highest number of frequencies. So let's do a couple quick examples, get your calculators warmed up. Let's just do a quick find the mean of the first set of data. Let's take a look at this top line. Say we have 4 points of data. The numbers are 1, 7, 3, and 6. See if you can find the mean, also known as the average of those four numbers.
4.25.
4.25 sounds good to me. Yes. So you can take those numbers, add them all up, divide by 4. Might be better if there's a button on your calculator that gives you mean. Is there maybe you might have a mean? Just glance at it, see if there's a mean button on your calculator. It'll be an X with a bar over it. It might look like this. Possible. It also might look like a U, sort of a cursive U.
So the next bar, W.
Well, if nothing jumps out at you, maybe you can explore that in the privacy of your own home. Let's go ahead and move on. Let's do a quick example. Median. Remember we said the median is the middle number. Let's take a look at this next set of data. This data set right here. Go ahead and find the median of this number, of this set of data. If you were to line them all up, what's the middle number? 1022? 1022. All right, so if you were to line them up, why do I have to? So, what do you have, Dr. Williams? Median of that number.
Yeah, 15.6. And right.
Nikita, what do you have?
15.6.
How do you get 15.6?
I added and then divided by 6, but we have to find the median.
Yes, you're looking for the mean, and you found the mean also, right?
Yeah, that's the mean.
Okay, so we want the median, which is the middle number. If we were to line them all up, and there is, what, 1, 2, 3, 4, 5, 6. So there are 6 numbers here. 1, 2, 3, 4, 5, 6. So this is a tricky one. There's going to be 2 numbers in the middle. And what were they?
10,
22. Well, let's line them up. Let's do 0, 7, 10, 22, 25, and 30. All right, so then let's take these two. What do we get if we average 10 and 22? 32, 16? 16?
16.
Yes. All right. So median in this case is going to be 16. Slightly tricky there. Let's find the median of this next set of data. This third data set. Find the median of that number for me.
5.5.
5.5. Let's see. I'm liking 5.5. Nikita? 5.5? Excellent. 5.5 is what I get as well. Moving on, we've got mean, we've got median. We're confident on those two terms. Let's find the mode in this next data set. Take a look at these numbers here and tell me what you get as the mode.
65, 65.
5. Nikita? 65. 65. Excellent. Perfect. 65 is the most common number. If we were to put them on a frequency diagram, 65 would be the highest point. Fantastic. All right, how about this last set of data? Let's find the mode of this set of data. Erase this, get this out of your way. Don't want to cause confusion. Mode. Yes, 240 and 220. So the mode, we cannot average them because essentially what we're going to have if we were to plot this is we would have two sort of humps in the frequency diagram. So averaging them wouldn't give us important information. What does give us important information are the two spots where we have these humps, right? Maybe we've got, I don't know, a bunch of tires that are failing after 1,000 miles, and then if they make it past that, we've got a bunch of tires that fail after 1,500 miles. And so there's something weird going on at those 2 points, which could be of interest to us. Fantastic. So we understand mean, median, and mode. Let's take a look at some examples if we were to put them on a frequency diagram. So let's suppose we were looking at some income levels of families in a certain residential area in, say, New Jersey, and we were to sample all the families and find out how much income each were earning, and we were to put all that information together on a frequency diagram, and we were to plot it. So okay, so we're to go out, we're going to collect a whole bunch of data, and on this horizontal axis, we're going to put family income, and on the vertical axis, we're going to put number of families. Number of families that have that much income. Okay. Now I'm going to draw, for the time being, what we'll call a normal distribution. And we'll talk more about that in a minute. But for now, we'll just suppose that there's a middle number, a mean, which is the most common income we have in this town in New Jersey. And we have a few people who make more than that. We have a few people who make less than that. And we have extreme rich people and we have extreme poor people. And we'll for now assume that it's an even distribution. Now suppose I were to tell you a few characteristics about this New Jersey town. Suppose I were to tell you the mean is 60,000, and I'm going to notate mean with this little cursive U. Mean is 60K. All right, also to tell you that the mode is 60K. And I'm going to tell you that the median is 60K. All right, so everything is 60K. And we're able to look at that distribution and we'll say, well, the average person in town makes $60,000. Half the people make more than 60,000. Half the people make less than 60,000. And the most common amount people make is 60,000. Now, let's look at it a little. So we're clear on that, right? Suppose that's the situation. Now let's throw a little wrinkle into it and say, suppose I give you slightly different information. Suppose I were to tell you that the mean in this town is 60,000. Suppose I don't give you information about the mode. Wait a minute. Now I'm going to tell you the median is 60K, but I'm going to tell you that the mean is 85K. Okay. So the mean income in this town is 85K. The median is 60K. How are you, as statisticians, going to interpret that information? What does that mean?
The average household income is 85,000.
Yes. What else? How do we interpret this median of 60K? What's the definition of median? Middle number, right? So half the people make more than 60K, half the people make less than 60K. But the mean is higher than the median.
So it's between 85 and before 60, so somehow between 55 to, let's say.
What is? I'm sorry.
Like lower than 60 and higher than 85.
I'm sorry, what are you saying? What is?
Somewhere between 85 and the other number will be like less than, the middle number should be 60. That is the only clear.
Okay, I'm not sure what you're saying. So we've got the median, the middle number is 60, so half the people make less than 60, half the people make more than 60. But if we were to add up everyone's salary and divide by the number of people in the town, we would get 85,000. And what I want you to do right now is think about, how do we interpret that data? Does that mean we've got a bunch of really rich people, a bunch of really poor people? Do the rich people make a lot more? Do the poor people make a lot less? I mean, how do we interpret that just based on those two pieces of information?
Rich people make a lot more.
Okay, so what do you mean by that?
Well, there's got to be a higher, because if the mean is 85,000 and the median is 60, that means it's really increasing significantly beyond the median.
What's increasing significantly beyond the median?
The salary. There's got to be some really high salaries to bring that average $25,000 above the median.
There's got to be some really high salaries. Okay, I'd agree with that. See if you can, Sanjay, can you sound that out a little bit more for us? What are we saying when there's got to be some really high salaries? What does that mean for this normal distribution?
Trying to figure it out.
Kita?
In calculation, I was adding together and then dividing by 2. So I got like 72.5.
Okay. It's exactly what Dr. Williams is saying, is that there's some really high salaries. So the folks on this higher edge are making a lot. So maybe there are people who are making above the average income or above the median income, and they're making a lot more relative to the people on the low end of the scale. You might say the rich people are really, really rich, and the poor people are kind of poor. So suppose if we were to look at our normal distribution and we were to say, okay, so if we were to look at these as a series of points all along this distribution, and we were to say all of a sudden, all right, this person gets a raise, okay, and this person gets a raise, and this person gets a raise, and this person gets a raise, this person gets a raise, and this person gets a raise. All the rich people get a raise, all the poor people make the same amount of money. So we haven't shifted the half of the people who are above in the top earning income, or the half of the people that are below. All we've done is given the rich people a little bit of a raise. And that's why we're going to have a higher mean than the median. So let's look at this from the opposite direction. Suppose I were to tell you this information. Suppose I were to tell you that the mean in this town is 45K, and the median is 60K. How do we explain that information? Suppose we're looking at this town as a possible place where we might develop our business, possible place we might go to market our products. And we gather or research and we find this information. How do we interpret that for, say, our investors? Mean is 45K, median is 60K. Brandon?
Would it show that there's more low-income families in that property as opposed to higher income?
Okay, so you're saying there's more low-income families than high-income families. Okay. I'm going to use this as an opportunity to say we need to be careful with how we say that, because half the families are below 60K, half the families are above 60K. So there's not necessarily more families in the lower half. There's half, exactly half. Question is, how are those families in the low part of the income affecting the mean?
They have very low income.
Yes. So the families in the lower half part in a very low income. You sound that out a little bit more, Dr. Williams?
Well, to make the average 45,000 and the median 60, you've got to have a lot of people that are not making anywhere near $45,000. And you have a number of people that are making over $60,000 or whatever it is to kind of bring that mean up to $45,000.
Nikita, do you want to summarize that again for us? Sanjay?
So you have 20 families, 10 on the right-hand side, 10 on the left-hand side.
Sure.
And you have the right-hand side being the high-income families. Those families make significantly higher salaries than the family on the left-hand side, the low-income families. To get the average up to 45, so like,
Dr. Williams.
Dr. Williams. So say they're making the 10 families on the left-hand side are making 20,000, and then you would have 20,000 a year. The families on the right-hand side would make, say, 60,000 or 80,000 a year, and when you add them all up, the average would be, the mean would be 45K or something like that.
Okay, I think you're absolutely on the right track. I know at least at one point, I feel like you got the numbers slightly backwards. So the families on the left-hand side are really, really poor. The families on the right-hand side are, you might say, rich in a modest fashion. So we might have some cases of extreme poverty in this town. Alternatively, we might have, actually, no, we'll just say there are cases of like extreme poverty in this town. So even though half the people are below 60,000, half the people are above, there's folks who are just pulling that average down. Might be something for us to be careful of if we are going to market our products there. It also might be, say something about the job market or employment if we're going to build a new factory in this town. All right. Well, let's do some more examples with this. Mean 60, median 50. Okay. So what if, what if I were to tell you the mean is 60K? Alright, I were to tell you the median is 50K. And then I were to tell you the mode is 4K. Take a look at that town. I'm going to erase this frequency distribution so you don't get confused. Mean 60K, mode 4K, median 50K.
So the average income is 60,000. Most people pay 4,000 a year. Right? So
Do most people make 4,000 a year?
Not most people, but in the community you have a number of families. So say if you have a family of 20, you probably have a family of 5 that makes 4,000 a year, and the other 15, their salary is different.
So the most common number is
yes.
4,000. So there's a chunk of folks who make 4,000. Now it doesn't mean the most people make 4,000, but it's potentially significant for us to look at. So all right, so we've got a chunk of folks making 4,000. And then how do we interpret these other two numbers?
60,000 is the average.
Okay, so we add them all up, divide by the total number, we get 60,000. And then how do we interpret the median? Or how does that affect our view of this town?
Half the town makes over 50,000, the other half makes less than 50,000.
Yes, yes. So I might look at this and say, even though there's a sizable poor population making 4,000, which is very low, right? Alarmingly low. We might look at those numbers and say, what's going on there? Maybe there's government assistance where a bunch of folks are making 4,000. Maybe it's a retirement community where a bunch of folks are making this small amount. But I would also look at these two numbers and say that even though there's a sizable chunk making 4,000, it's not really pulling the average down significantly. And in fact, we've got a number of folks in the very high income who are pulling the average up.
Well, I would say this is a university town with a lot of poor students and highly paid faculty members, particularly in the business school.
Okay. A lot of poor students, perhaps. Good analysis. Right? Median is still around 50K, and we've got highly paid business school faculty who are pulling the average up. Okay, let's continue with this. Let's say mean 60K, mode 4K, median. All right. Let's take a look at this. Median now is 5K. So we've got an average income in the town of 60,000. Mode, meaning the most common income, is 4,000. And now I'm telling you that the median is 5,000. What does that mean? And how is that different from our previous example, where we said the median was 50K, the other town. Other town. It's potentially a tough one. Let's think it through. How are these two towns different? One with the median 50K, the one with the median 4K. They're not different because they have a different mean or a mode. They have the same mean and the same mode. The only difference is the 50K and the 5K median.
Half the town makes over 5,000 a year. The other half don't make less than 5,000 a year. And the other example, half the town made over 50,000 a year.
Okay, so how might you explain that? Is it a retirement community or a bunch of students? If there are a bunch of students, how big is that student population? Is it just a lot of poor people? And if there's a lot of poor people, is it a big chunk of poor people? Small chunk of poor people? What effect do they have on the average? A lot of it's going to be guesswork, but let's just think through some of the possibilities.
But based on the average, you have a lot of poor people, but you have
Wait, the average we have a lot of poor people?
No. I mean, you have a lot of, based on the mode and median, you have a lot of poor people, but you have quite a few rich people. That brings the average up to 60,000.
Okay, you said we've got a lot of poor people. I agree with that statement. But do we have a lot of rich people?
Well, the average is 60,000.
The average is 60,000. Does that mean we have a lot of rich people?
Well, you have a few rich people to bring the average up to 60,000.
Do we have a lot? Do we have a little? Do we have a few?
I'd say a few.
A few.
Yes.
All right. This is what this median of 5,000 tells us, that we have a small number
Population
of really, really rich people. Because half the people make less than 5,000. In our previous example, it wasn't this extreme. All right, half the people make less than 50,000. And we can take these two numbers together, perhaps, and say there's a lot of people at this 4,000 range, perhaps because of a retirement community, perhaps because of government assistance. We might do some further analysis. But taking these two numbers together tell us that this is half the people in this town are in this range, are strongly affected by this. Now, at the same time, something is happening which is pulling the average up to $60,000, even though half the people are less than 5,000. And that something is what, Sanjay?
Yeah, a few rich people.
A few super, super rich people. We can tell a lot just by looking at these three numbers, right? Potentially. Which might help us with decisions if we're doing business analysis. Or say we're working for one of the presidential candidates and we're trying to decide where to spend advertising dollars or how to market our campaign successfully. These three numbers can tell us an interesting trend, can tell us more than we might have thought of. Let's take a look at a couple other examples. Actually, let's just go back now. Let's do those two that we talked about at the beginning. And let's just make sure we're clear on those. Because that last one with the mode of 50,000 and then the medium of 50 and then the median of 5, that's more of a nuanced one. one I want you to have a good grip on. The two I want you to have a good grip on. All right. The mean of 60 and the median of 45K. Let's just revisit what that means. I give you those two numbers. In this town, mean income is 60,000. Median income, wait a minute, sorry. Wait a minute, sorry. Got those backwards. Mean 45K, median 60K. I could have done it the other way, but just so we stay consistent. Mean income, 45K, median income, 60K. How do we describe what might be going on in this town? Brandon?
There are people in this town that are making less than 60K.
Yes.
So,
How many of them are making less than 60K?
There's more than half are making less. No.
Exactly half are making less than 60K.
So half are making less than 60K.
Yes. How do you know that exactly half are making less than 60K?
We go by the median.
Yes, the median. So exactly half are making less, exactly half are making more.
But okay, so since they're half are making less than 60, the other half making above 60, the ones that are making less than 60 it's really low because it's bringing down the mean.
Yes, the poor people are really, really poor, and they're bringing down the mean. Make sense? Okay, and then the
Well,
other...
it really wouldn't be that poor if the average is 45, though, right? Not necessarily.
Okay, so I may not be justified in saying that the poor people are really, really poor, but what we are justified in saying is that the poor people are having a larger effect on the mean than the rich people.
That's true.
The half of the people that are considered in the lower half are having a larger effect on the mean than the half of the people who are in the upper half. Okay, and then the opposite of that, we said the median is still 60. Then let's say the mean is 85K. How do we explain that? Nikita?
Average people are making, like half of the populations are making 60.
Half of the people are making...
Few of the people are making 60, but more people are making, more people.
Okay, so what does the median of 60K tell us? What's the definition of median?
Average, minimum,
Which one?
60K.
What's the definition of median? You gave me two things. You said average, and then you said middle number, and I said which one? Middle number, yes. Okay. So the definition of the median is the middle number. And in other words, that means...
Half of the middle number are making 60K.
Middle number, okay.
60. So, like I said, if
The middle, it means there's the middle family is making 60K. Wait, so is that all you're going to tell me about?
Yes.
That's all you're going to say?
And there are more people who are making like a lower class, poor people, have a lot of poor people.
Okay, so you just told me that the middle number is 60K, but there are more people making less than 60K. Okay, is that correct, Sanjay?
The middle number, the more people.
Okay, the statement that Nikita is making is the middle number is 60K, but there are more people making less than 60K. Is that correct, Brian?
No.
It is not correct. The middle number is 60K, which means half the people are making less, half the people are making more. It's definition of median. you line up everybody in town, you're correct. The middle number is 60K. But that means half the people are making less, half the people are making more. Question is, why is this mean 85? Why is it above the median?
You have a few people in the population that makes significantly higher than $60,000 a year.
A few people in the upper half
In the upper half.
were making much more. So if we were to look at the frequency distribution, this might be a normal distribution with, a mean right here at 60K, alright? But that's not this town. What's happening in this town is that there are a few people in the upper half who are making a little bit more. Alright, all the rich people got a raise. That example we went through earlier, or the example I mentioned earlier. So we might draw this frequency distribution like this. It would be a little elongated like that. And we call that right skewed. All the rich people got a raise. There's more extreme outliers on the right-hand side. The median could still be at 60K. The mode could still be at 60K. Sometimes there's a little variation. But all we're saying with this right skewed data is that all the rich people in the upper half got a little bit of a raise relative to the people in the bottom half. Make sense? Alternatively, let's go back to this other example. Mean in this town is 45K. Median is 60K. Half the people are making above 60K, half the people are making below 60K, the median. But we know that because the mean is lower, the people on the lower half are pulling that average down. It's not that there's more of them. It means that for some reason they're pulling the average down. Like all the poor people lost a little bit of their income. Or there's a poor tax. I don't know. Is that a thing? Poor tax may be a thing from centuries past. So this distribution might look like this. It would be elongated on the left side. Something like that. Let me draw that a little more accurately. So all the poor people lose a little bit of their income, and we're going to call this left skewed. Makes sense? We've got, yes?
So, mean is 60K and median is 60K.
I'm sorry?
Are the mean and median both is 60K or the 60K?
No. In this example, the median is 60K. The mean is 45K. So we've got a bunch of extreme poverty pulling the mean down. We're going to call this left skewed. So we know left skewed, and we know right skewed. Left skewed, mean is pulled down. Right skewed, the mean is pulled up. Any questions? All right. So let's go back to just a normal looking distribution. let's forget about this being a weird town where there might be university students or professors making exorbitant salaries. Let's just say everything is distributed more or less what we would call normally. Now, normal distributions have some very interesting properties. One, the mean, median, and mode are all at the same spot. So the mean, median, and mode are all at this high point in the center of the graph. Normal. The other interesting thing is that it is symmetrical on either side of the mean. I may not have drawn that perfectly, but that's the normal distribution. And the normal distribution, absent weird things going on, is very interesting to us. It tells us how variations work essentially in the natural world. And scientists have researched this, and they found that naturally, data will distribute in this fashion. If you were to look at the size of planets in the whole universe, you were to add up all the sizes of various planets everywhere in the whole universe, you would find an average, and you would find a normally distributed frequency distribution. Some would be a little bit bigger, some would be a little bit smaller, some would be really, really big, some would be really, really small. It would naturally fall into this distribution. And this is not something that scientists or statisticians made up. It's something that they discovered. They discovered that there was a certain way that this breaks down. And in order to flesh that out, there's one more thing I need to tell you, one more piece of information I need to give you about how data is distributed. So let me do that. Make myself some room. Okay. All right. So suppose I were to show you one frequency distribution that looked like this. Okay, so we have number of families, number of planets, whatever, and we have amount of income, and we have number of families. All right, this is one option. And then I'm going to show you another frequency distribution that looks like this. How would you describe the difference between these two frequency distributions?
The one on the right is the normal distribution. And the one on the left is skewed to the left.
Wait, this one is skewed?
Yeah.
All right, I meant to draw this symmetrically.
Oh.
So sorry. So we'll say that this is symmetrical.
Okay.
My bad.
The other
Now.
one is symmetrical too.
Yes, they are both symmetrical.
Okay.
They're both symmetrical about the mean. All right, so suppose this is the mean. This is the mean. Those are mirror images of each side. But there's still something different about this one. We'll call this A. And we'll call this one B. There's still something different about A and B. What?
So you said the what is the x-axis, right? The horizontal
Yes.
line. What is that? That's the income.
This could be income. It could be size of a planet. All right, and on this axis is number of families with that income or number of planets with that size.
So using income as an example, example A. So say the median was 50,000.
Yes.
With example A, the income slowly decreased as you're going down, and with the other one, it drops almost immediately. The example would be.
Yes. That's it. That's what I'm going for. In this example, there's more variation in income. There's a wider dispersion of the data. In this, there's less variation. So we've got a most common amount of income, maybe it's say 60,000, and then by the time you get down to 50,000, there's pretty much no one making less than 50,000. By the time you get up to 70,000, there's pretty much no one making more than 70,000. So pretty much everyone in the town is making between 50 and 70,000. In this town, all right, we've got a big chunk of people who are making 80, 90K, and we've got a big chunk of people who are making 20, 30K. So the dispersion of the data is wider in town A, and it is narrower in town B. And we measure this dispersion with a certain metric. Does anyone remember what it is from their statistics course? Standard
deviation.
Yes. You got it. You knew it. Standard deviation. All right. Deviation is the dispersion of the data. And I'm going to tell you the mathematical definition of that, and we'll just work out an example, but do not get scared by these numbers. It is the variance of each individual point of data from the mean. And we don't care about whether or not that variance is above or below. We don't care if it's positive or negative. So we do something a process in which we take the square of that variation, and then we take the square root of all of that. So, the standard deviation, signified by this little symbol, an O with a salute on the top of it, equals the square root of the sum of x bar minus, let me get this right, x minus the mean squared divided by n. Okay, so that little u, mu, is the mean of all this data. X is each individual point of data. So we take the difference between those two and we square it. And we don't care if it's positive or negative difference. We just care about the difference. And we divide that by n, the number of pieces of data. And because we squared this up here, we take the square root of everything. And that's going to give us our measure, a number, which tells us the standard deviation. So let's just do a quick, easy example. I'm going to give you 3 numbers. I'm going to say, let's get the standard deviation of these 3 numbers. Let's call it 3, 6, and 7. So suppose we did some sort of sampling, and we needed to find the standard deviation of those 3 points of data. How we're going to do that is we could punch them in individually in our calculator. The first step is to find the mean of this data, right? We had 3, 6, and 7, which gives us 16. Divided by 3 is 5.333. So then we go with each individual number. 3 minus 5.333 squared plus 6 minus 5.333 squared plus 7 minus 5.33 squared divided by 3. Nikita? X is each one of these. So each piece of sample data. clarify, this is going to be our population standard deviation. $37, that's not correct. And I can tell you that's not correct for two reasons. One, because I know what the answer is, and that's not it. But I can also tell you that the deviation between these three numbers is not that much. So we've got 3, 6, and 7. So the deviation between 3 and 6, that's 3. Between 6 and 7, that's 1. Between 7 and 3, that's 4. So it's going to be a number between somewhere on the 1, 3, 4 range. Did you forget to square root the whole thing at the end? Maybe you added up everything and then forget to take the square root? You have it, Brandon?
I'm not sure. I got 2.94.
Okay, that's the closer range, but that's not the answer I've come up with. Sanjay?
I'm still working on it.
Okay. What would be better is if your calculator actually had a standard deviation button.
So 1.8.
I like 1.8. I get 1.7. Did you take the sample? I bet you took the sample standard deviation, and you got a little bit higher.
Yeah, I got 1.7.
What'd you get?
I got 1.7.
1.7, yes. I like 1.7. Let's see what I'm asking you to do on the quiz. Okay, 1.7 is the answer I come up with. So instead of cranking it out on your calculator, if your calculator has a shortcut, I would figure out how to do that. The other option is Excel. So you can put these numbers in Excel, put equals population standard deviation. Now I just mentioned there's a slight difference between the population standard deviation and the sample standard deviation. Let's go over sample standard deviation really quick. So sample standard deviation is a little bit different than the population standard deviation. If we have the entire population of numbers, say 3, 6, and 7, we can calculate the variance. We put it in a number, which we called, in this case, 1.7. That's if we have every single number in the population. But a lot of times we don't have every single number. We just need to take a sample. And because we only have a sample, we're working with partial data. So we make a very slight adjustment with the sample standard deviation, and we make it a little bit bigger to account for the possibility of error. Think you did?
I think that's still standard deviation.
1.7? All right, so well, let's do it. So we said the down on one knee here. So we said the mean was 5.33, right? Did you get that far? Okay. So we want 3 minus 5.33 squared, right? Right? Plus 6 minus 5.33 squared plus 7 minus 5.33 squared. All divided by what, Nikita?
3.
3. And what do we do after that? What?
I didn't do like this one. That's why I didn't get that answer.
After we do that, we take the square root of the entire thing. And that should get you 1.7. Now, this is population standard deviation. Now suppose we don't know the entire population. We're going to make a slight adjustment, and we're going to calculate what is called the sample standard deviation. Sample standard deviation. Standard deviation. All right, it is denoted by the letter S. Small s equals the sum of the individual pieces of data, the difference between that and the mean of the sample data, which is denoted by this x with a bar over it, squared, divided by, instead of n, we're going to divide that by n minus 1. And then we're going to take the square root of the whole thing. So this x is each individual piece of sample data, and this x bar is the sample mean. Write this over here. X bar equals sample mean. Now, because we don't know the population mean, we don't know this u, we have to average our sample, and we use that as our estimate for the mean. We'll call that the sample mean. And by adding up the sum of the squared differences and dividing by n minus 1, instead of dividing by n, it's going to make that number just a little bit bigger. And why do we want that number to be a little bit bigger? Dr. Williams?
Well, it's advantage of the error possibilities.
Account for error. Is that what you're going to say, Sanjay?
No, I was going.
Okay. All right. At least you're honest. So to account for the possibility of error, we make it just a little bit bigger. Okay. So let's try to find the sample standard deviation for these three numbers. And let's not spend too much time on it. 3, 6, 7. Does anyone have a shortcut on their calculator? It would be that letter, the small s, on their calculator. If you have the shortcut, we'll do it. If not, we'll just... Okay.
542.
I get 2.08.
I thought it had a small s on here.
All right. Well, that financial calculator just need to figure out how to crank it out. All right. Good. I want to just take a look at a couple examples in the textbook, and I think there are sample standard deviations. Page 554, number 24. correction, page 543. Page 543, number 24. Okay. These are calculations of sample mean. So you will have homework problems like this. I suggest you put these in Excel and just use the function for sample standard deviation. And remember, there's a difference between population standard deviation and sample standard deviation. Sample standard deviation, a little bit bigger to account for error. All right, so let's move on from standard deviation, and let's look at just a couple of problems to review the material that we went over previously. Let's turn to page 523. All right. And let's look at those shapes. On the bottom half of page 523, let's look at A, B, C, and D. All right, first let's look at A. I guess I didn't really explain this. This is called a uniform distribution. You can see in example A that there are a certain number of values, and they all have the same frequency. What might be going on here is, suppose in this town, this very strange town, you might have a chunk of employees that make $10,000, another chunk of employees who make $20,000, and another chunk who make $30,000, another chunk who make some slight variation of that. And this distribution looks what we call pretty much uniform. And again, this is income, right, and number of families. So this might be a weird situation where there's just a certain chunk of people who make the exact same income and who work at one company, and a certain chunk of people who make pretty much the same income, maybe a little bit higher, at another company, and there's maybe 3 or 4 companies like that, and then there's no room for anybody else. There's no room for really rich people, no room for really poor people for whatever reason. In which case we would call it a uniform distribution, where we have certain income levels, and there's the same number of people at each of them. And we would call this a uniform distribution. Uniform distribution. Okay, so I just had to go over that really quick because I didn't mention it when we were looking at different types of distributions. So the answer to A on page 523 is that's a uniform distribution. So let's take a look at the next one, B. Your options are uniform, which we just went over, normal distribution, which we talked about. We also talked about left skewed. We also talked about right skewed. So B is that uniform, normal, left skewed, right skewed.
Normal.
Normal? Normal? Normal, Sanjay? All right, fantastic. How about C? Is that uniform, normal, left skewed, right skewed? Left skewed, okay. So we've got a longer, fatter tail on the left side. Sometimes people get confused because the hump is over to the right.
Yeah, I was looking at the wrong one.
Oh, okay. So C, we're looking at C, and the hump, oh, you were looking at the wrong one.
Yeah, I was looking at the wrong
You're the wrong one and you got it right.
No, I got it wrong.
Okay. What did you right?
No, because I said right.
Okay.
Yeah.
Okay. So it's left skewed because the tail on the left side is longer and fatter. What that means in our
Be fatter. I can see it's longer, but not necessarily fatter.
thicker,
Like it's
higher. When I say fatter, I mean higher.
on the left skew.
Yes, on the left side. So if I were to use this diagram as an example. So this is a normal distribution. And if I were to make this left side a little fatter, I would make it higher, sort of higher like this. So this is pushed up a little bit on the left side. That's what I mean by fatter.
Okay.
You'll hear the term fatter
But
tails.
that's not what C looks like though. On the picture we have, it doesn't look fatter, it looks longer but not fatter.
Fatter. How about this? What if I were to draw it like this? Huh?
That's better, but it's still, you know, if you look at it, it still is, it's thinner, but it's longer. It's hard to say it's fatter.
So, okay. So we could call this part a tail. Maybe that's not the extreme tail, but
It looks like it's going down on the y-axis substantially as you go. It's not going up on the y-axis, it's going down on the y-axis and out.
so, all right. So we've got the tail on the right side. What I want to do on the left side is I want to make it higher. All right. On the left side, I want to make it higher. If I were able to draw the left side with the tail up, would you agree with me that that's a fatter tail?
If the tail's up, right?
Yeah. So if instead of, so I'll draw it just like this. So this is, let me start fresh here. All right. Okay, so I've got a fairly normal looking distribution right there. Now, I want to call it left skewed. I want to draw it so that this tail is fatter on this side. So I'm going to erase the red part. I'm going to erase my outline, which was just to guide me in this drawing. And I'm going to draw it like this. Fatter tail on the left side.
Okay, I agree with
Okay.
that. But that's not in the picture here, though.
Yeah, that's what the whole thing we just did. We just recreated the picture. We made a fatter tail on the left side.
Okay.
Yes. Fatter tail on the left side. Longer as well, maybe, is your point?
Yes, that's what I was
It's not only
focused on.
fatter, it's longer. Now, one thing that I didn't stress in a theoretical frequency distribution is the tails go on forever.
Yeah.
There's some possibility of someone making 10, 20 billion, zillion dollars. It's very, very small, but there's a possibility of it. I guess there's a hard stop at 0 in this example. So the tails extend forever in theory. It's just they get a little fatter at the end. All right, let's take a look at D. What do we see there? Right skewed? Like right skewed? Fantastic. Okay, excellent. Let's turn to page 526. Let's look at number 22. Same thing. What do you see? Uniform, right skewed, left skewed, normal. Uniform? 22. You see that big bar on the right, on the left-hand side? You see those small bars on the left-hand side? So I would say, just based on that, it's not normal. Or it's not uniform. You said uniform, right?
22.
Yeah, 22. Page 526. What do you think, Brandon?
That's all right.
Sanjay? Dr. Williams?
Right.
Yes, right skewed is correct because it's got a fatter tail on the right side. 23. See, left skewed? Left, yes. 23, and 25. And what did I want to do? 25. Describe the shape. What do you see on this shape?
25 or 24?
25. Did we already do 24?
No.
We skipped 24. Let's skip 24. 24 is normal. Let's look at 25. Yeah, I'd say right skewed. You could make an argument, but right skewed, especially because it has that fat tail on the far right. And it just drops off on the left side.
It's a longer tail, but not necessarily a fatter tail. Am I wrong about that?
Yeah, remember the length goes on forever?
Forever, yeah.
Yep, so you can't say longer. Okay. We are rocking and rolling. Let's take a quick break, and then we'll come back and we will do z-scores. Let's come back. Do you want are you okay with a short break? Yeah, short break. Let's come back at 7:50, and we'll power through the rest of the material. A 7-minute break. The 1.7?
Yeah.
Yeah. Ew, what's that? So like 300.
49.
And you got 1.07?
No, 10.07. This is the correct answer.
Plus, minus.
Standard
Minus.
deviation is minus.
Minus, yes. Minus.
That's fine.
Minus. And really, you want to just do this on Excel.
Oh, okay.
I just practice on the calculator.
And
just to
what
mess
is,
around.
for the sample now? What is
So this is assuming that that's just a sample.
Mhm.
We don't have the entire population. We only have those 3 sample data.
Okay.
So we can't say that the mean for the whole population
Mhm.
is 5.33. All we can say is the sample mean is 5.33.
Okay. So sample mean is the same as whatever we did on the median? Sample mean and the mean is same, right?
For the calculations, it's
Yeah.
the same.
Okay.
Yes.
Thank you.
Yeah. All right. Think about how I'm going to present this next piece. let's finish this up, or move towards the second half of the data. I think Brandon will be able to catch up with us. So we talked a little bit about this normal distribution being something interesting. And I mentioned that this is something that scientists discovered. It's not something that scientists created. They found in nature variations distribute normally. I used the example of planets. It's the same of sizes of trees in a forest. If you were to take 10,000 trees in a forest, measure how tall each of them are, you would have an average, and you would have some that are a little bit higher than the average, some that are a little bit lower than the average. And as long as there's not something weird going on, like some radioactive plant that's affecting the size of the trees, then you would see a normal distribution. If you conducted some sort of experiment yourself, such as measuring the size of trees yourself, you could find this normal distribution as well. And this is interesting, because data didn't have to be distributed like this. It could have looked different. It could have been linear, right? Maybe, the average size of a tree in a forest might be, that, and then it might be a straight line down, right? That might be the distribution, right? Who are we to say that that's wrong? But data distributes normally. It is something of a law of nature, and because we've studied it, and we know, we can say things about the way this distribution works. One of those things we can say is the amount of data within one standard deviation of the mean. So say the mean of this data is a normal distribution of male height. All right, normal distribution, let me put that title. Male height. Male H-E-I-G-T. All right, in the mean, the average male height is 70 inches, and the standard deviation is 3.5 inches. We know, if this data is normal, and we do, that within one standard deviation is going to be 68.3% of the data. So 63.8% of males are going to be within one standard deviation of 70 inches tall. What that would mean, numbers-wise, we would take 70 inches minus 3.5, and we would get 66.5 inches, right? And 73.5 inches. We know that 60% of the people in the world, males in the world, are going to be between those heights. Similarly, we also know that within two standard deviations, it's going to encompass 95.5% of the data. How do we know this? Because this is a law of nature. That as long as there's not something corrupting the data, as long as there's not something making all the males really tall or all the males really short, that there will be an average, and it will distribute based on the standard deviation. But once we know those two things, we know that the data will distribute normally. And we know 3 standard deviations as well. I think 3 standard deviations is 99.7. 3 standard deviations is 99.7% of the data. Now, we can break it down further than that. If we were to ask any male how tall they are, we would be able to tell them what percentile they are within the entire population. And how we standardize a normal distribution is with something called a z-score. I know, Sanjay, we talked about this before class. Has anyone else heard of a z-score before? Nikita, have you heard of a z-score? Brandon, have you heard of a z-score?
Briefly.
This just tells us how many standard deviations a sample is above or below the mean. So, if If I were to tell you my height is 73.5, it's not, but if I were to tell you that, that would be exactly one standard deviation above the mean. And we would assign that a z-score of 1. If my height were, what's 3.5 times 2? 77 inches, I would be 2 standard deviations above the mean. And I would have a z-score of 2. Now, if my height happened to be 70 inches right on, I would not be above or below the mean, and I would have a z-score of 0. If I were to have a height below, I would have a negative z-score. If I were to be 1 z-score below, if my height were 66.5, my z-score would be negative 1. And based on the z-score, and knowing what we know about the way data distributes normally, we can make various assumptions about how likely it is to have that height, and what percentage of males have a lower height than me, and what percentage of males have a higher height than me. And the way a z-score is calculated is the sample itself, such as my height or your height, minus the average, the population mean, divided by the standard deviation. So I gave the example earlier. If my height was 73, my z-score would be 73 minus the mean of 70 divided by the standard deviation of 3.5, and that's going to equal 73.5. So I'm 73.5 inches tall. Minus 70 is 3.5 divided by 3.5 equals a z-score of 1. Make sense? All right. Do any of the males in this room, would they like to share their height?
66 inches.
66 inches? All right. Let's do it. Not to pick on you, Sanjay, but I wanted a negative z-score. So 66 inches. 66 inches minus the average of 70 divided by the standard deviation of 3.5. What does that give us? Minus 1.3? 1.14. Okay. So that is the z-score minus 1.14. So what we can do is we can actually look at a table which gives us percentages for any normal distribution, and we can tell Sanjay what percentile he is in based on his z-score. So let's do that. Let's take a look in the back of your textbook at the z-table, which is going to be on page 860. Now, 860. Now this is a little confusing because we're given the positive z-scores, and we need to turn around and think of the negative z-scores. So if you look in the far left-hand column, you've got Z, and then you've got A. So the z-score is the actual z-score that we just calculated, and right next to it is A, the area under the curve from that z-score. So let's look up, we can look up 1.4. Let's start by looking up, we can't look up negative, so let's start by looking up 1.14. So we scroll down the first column, we go over to the next column, we go over to the third column, you just see where I am? And we get 0.3729. Okay, so what that means, 0.3729, that is if we were to look at just the upper half of the normal distribution, and we were to look at the z from 0 to 1.14, that chunk is going to be, what is it, what was it again, 0.3?
3729.
3729. So 0.3, we'll call it 0.3, so we'll just call it 0.37. So between 0 and 1.4 of a z-score is 37% of the data. Remember we said plus or minus 1 is 68% of the data? Now we're just looking on the positive side. Between 0 and 1.4, 37% of the data. That's the first step because the chart is only in positive numbers. It's identical on the negative side. So, negative 1.14 also encompasses 37% of the data. So, question now, what percentage of males are shorter than Sanjay? 37? Below 37, exactly. All right, it's this junk right here. All right, that is the percentage of males that are shorter than Sanjay. And what is that? Okay. We know that this is normally distributed, so the mean, median, and mode are all in the same spot. It is symmetrical on either side. 50% of the data is above, 50% of the data is below. And I just told you that this chunk between the middle and negative 1.14 of a z-score encompasses 37% of the data. How much data is below the mean? What percentage? 50%, okay? So this whole thing here, starting here, going all the way here, 50%. And this chunk here, 37%. So what's this chunk here? You got it? 0.13. So 13% of males are shorter than Sanjay. Now, we're going to open up this door and wait for the next male to walk by. This is not scientific, but just work with me for a minute. What are the chances that the next male who walks by is shorter than Sanjay?
Slim.
How much?
13%.
13%. 13%. Now, the sample is a little bit biased. Maybe, people who hang out at Mercy College are on the average taller. People who get their MBAs are a little shorter than the average. So it's not an unbiased sample, but that gives you an idea of how we can use this data. So let me throw in a couple other numbers here. Let's see, we know Sanjay is 1.4. Let me tell you how tall Michael Jordan is. Michael Jordan is 78 inches tall. All right, MJ is 78 inches tall. Can you tell me Michael Jordan's z-score?
.28.
I like it. Z-score equals 2.28. Everyone get that?
Mm-hmm.
Yes. Okay. Next question. What percentage of males are taller than Michael Jordan?
2%.
2%. How are you getting that?
0.48.
What? From the chart? Okay, so we're looking on the chart for 2.29 or 2.28, And when we get to 2.28,
0.4887.
faster than me, 2.28, yes, 0.4887. Okay, so that is about 49%, right? And what does that 49% mean?
Taller than,
Say again, Nikita?
taller than Michael Jordan.
49%? And remember that that data is just half of the distribution.
Oh,
All right. So okay. So tell me, how do I interpret? I'm going to keep this 37 up because we're going to use this 0.37. How do I interpret Michael Jordan? I'm going to tell you is in this half of the distribution. All right. And you got a z-score of 2.28, and you told me area under the curve 49%. So what is that? 49% of the whole thing. So that means just 51% of the people are taller than him. No.
1%.
What's that?
1%.
1%, exactly. So it's this section right here is 0.49, and this section right here, 0.01, taller than Michael Jordan. Next question. What percentage of males have a height in between Sanjay and Michael Jordan?
Twelve.
12% are between Sanjay and Michael Jordan? Oh, I see what you might have done, and you're definitely on the right track, but that is incorrect. So Sanjay is fairly low on the population distribution. There's only 13% of males who are shorter than him. And Michael Jordan is pretty high. There's only 1% of males that are taller than him. And you're telling me that there's 12% in between those two? I'm going to tell you that it's more.
0.57.
157%?
0.57.
0.57. I don't like 0.57. I like it a little better than 12, but I don't like 0.57.
$38.
38. I like that better than 12. I don't like that as much as I like 57. But I don't like that. Where are you getting 30?
Well, 13% is shorter.
Yep.
So 37% are what's between.
Yeah. Okay. Now that you told me you're thinking, I like that a little more. It's still not quite right. But what you did is you said, all right, 13% is lower. So this chunk I know is between me and Michael Jordan,
Yeah.
but you're missing another chunk that is also between you and Michael Jordan. This chunk
86%.
here. 86% of males are between Sanjay's height and Michael Jordan's height. So we add the 37 plus the 49, we get 86. Wait for the next guy to walk by here. We know there's an 86% chance he's going to be between those two heights. All right. Let's do a couple examples just to ingrain that. And then we're going to go through these examples. We're going to spend a good half an hour going through them because I want you to feel comfortable with this. But the good news is that that's everything. All right, that's all the information I'm going to give you tonight. We're just going to spend about a half an hour making sure you're comfortable with that. So let's take a look at page 555, number 22. Let's see. Let me do this. Let me read it to you. Let me give you a couple minutes to just think about how you might solve it, and then we'll come back together as a class and solve it. All right, so according to the label, a regular can of Campbell's soup holds an average of 305 grams, with a standard deviation of 4.2 grams. What is the probability that a can will be sold that holds more than 306 grams? So, as Campbell's Soup is making their soup, they pour soup into these cans, and maybe there's some sort of variation, maybe a little bit extra squeezes out, maybe the machines are running dry, so a little bit less squeezes out. It's not perfectly 100, 305 grams each and every time. There's some variation, and we know that variation can be accounted for with the standard deviation of 4.2. And you can look above and you can say we're assuming this standard deviation or this distribution is normal, so that we know all these great rules about percentages apply. All right, so just think about that for a minute. Try to calculate it, and we'll come back together as a class. Let's come back together as a class. The information we're given, the mean in each can of soup is 305 grams. Standard deviation, 4.2. Question is, what is the probability of a can having more than 306 grams in it? So this 306 is a little bit higher than the mean. So we know the point we're interested in is just a little bit above the mean here. Alright, so that or higher is of interest to us. So we're looking for the area under the curve of this much data. The way we're going to find out how much that data is, first we're going to be told that this is a normal distribution. So we know we can use a normal distribution z-score table. And let's calculate it. Z-score. So what are the numbers? What's X? What's the sample statistic? 306. Excellent. minus what?
305.
305 divided by what?
4.2.
Excellent. Equals what?
0.23.
0.23.
Mhm.
All right. What is the area under the curve for a z-score of 0.23?
0.948.
How much?
0.948.
0.948. Okay, and how do we interpret that based on this z-score and on page 860?
I think that's 0.94.
What's that?
I think that's 0.24 because that sums from the standard deviation come to 0.238.
So
So
you got 0.948
is for 0.24.
is what? The z-score is 0.23, right?
0.23.
0.23. So I did that's 0.24. Is it correct?
Oh, fine. Yeah, that's fine. 0.23, 0.24.
Yeah,
That's fine.
right.
Okay. Question is, what's the area under the curve? You got 94? 0.23. Is that what you got, Sanjay?
Well, 0.24 will give you 94. 0.23 will give you 91%.
0.23 will give you 91%. Right, but when you looked at, wait a minute, when you looked at the 0.24, I get 0.0948.
Oh, so 9%.
You scared me there.
Yeah.
94%. All right. So it's 0.0948, right?
Yeah.
Yes. Okay. Okay, so that's 9.5%. You need to think about where on this distribution that 9.5% is relevant. Is that this part right here? And you can answer that question by looking at the little graphic at the top left. That little shaded part, that's the information you're getting from this z-table. And z-tables are different. Sometimes they'll have negatives, sometimes they'll give you the cumulative. So you need to know how to interpret each. So the question remains, 9.5%. Is that this? Is it this? Is it this? Is it, what is it?
It's on the lower end, on the right hand side, all the way
The shade.
the shaded area.
This shaded area?
Yeah, all the way to the right.
Okay, so the whole shaded area is 9%?
All right, now I'm confused.
All right. Well, look at the graph at the top of the at the upper left hand corner of the page there. It's telling you, all right, that it's giving you. It's telling you that it's giving you this. All right, with a z-score of 0, between 0 and 0.24, it's giving you this area under the curve. And we know that a Campbell soup can that has 306 grams in it has a z-score of 0.23 or 4. Right? So we know that between the mean and the z-score of 0.24, which has 306 grams, is 9.5% of the data. Which in our case is this. Markers are dying on me. Yeah. I'm going to use red. In our case, it's this right here. That is 9.5%. That's what it's telling us. So the question that we're being asked is, what's the question we're being asked? 550.
More than 306 grams.
Yes. What are the chances that it will hold more than 306 grams? Okay, we're 5. What are we on? What page are we on? 555. Yes, number 22. What is the probability a can will hold more than 306 grams. Okay. So I mentioned that this green shaded area, that's the probability we're looking for. That's the answer to our question. We have two other points of data. This black line is the mean. So 50% is above, 50% is below. And we looked at the z-score, and we know that this red squiggly part, 9.5%. Which means that this green part is how much?
41%.
41.5%. There's a 41.5% chance. Or 40,
40
yeah,
and a half.
40.5% chance. 40.5% chance that a can will hold more than 306 grams. That makes sense. So nothing terribly complicated. It's just getting your head around the different moving parts. And this is as complicated as we'll get in this class, but having thought this through will certainly help you when you get to 601. So let's try another one. 24. Let's do 24. Okay. General Electric soft white 3-way light bulb has an average life of 1,200 hours with a standard deviation of 50 hours. Find the probability that the life of one of these bulbs will be between 1150 and 1,300 hours. All right, give some thought to that. We'll do that as a class. You got an answer? I don't know the answer, but I'm glad you have one. So, just finish up if you are close to the answer, and we'll think this through from the beginning. All right. So, we are testing these light bulbs. We know that the average life of a light bulb, 1,200 hours. They don't burn out exactly 1,200. Sometimes you get a light bulb that lasts really, really long. Sometimes you get one that just burns out right away. So we have information. One, we know that these are normally distributed. 2, we know the mean is 1,200 hours and the standard deviation is 50. We are asked, what is the probability of having this particular light bulb, one particular light bulb, last between 1,150 hours and 1,300 hours? So we know the 1,150 is below the mean, so it's on the lower 50% of the data. Okay, so let's just put a little green line right here. And we know that the 1,300 is above the mean, so we know that that's in the upper percentage of the data. And the question we're being asked are, what are the chances that the life of a particular light bulb will be between those two? So what area under this curve, Sanjay, is going to answer that question? Is it going to be this area? This area here?
Between the two green lines and the
Yes, everyone see that? Between the two green lines is the answer we seek. The knowledge we seek is between these two green lines. So, if we didn't know this was normally distributed, we might have some trouble. We'd have to do some calculations. But we do. And also, we know that scientists have discovered how data normally distributes given normal circumstances. So all we have to do at this point is we need to find a z-score for this 1,300, and we need to find a z-score for this 1,150, and we need to interpret what that means in terms of these chunks of area. So, do we get a z-score for 1,150?
It's 0.34.
0.34?
13. 0.3413.
0.34. All right, 0.34 is close enough, but I can tell you, I'm sorry?
This is from the chart.
This z-score?
Z-score is -1.
Okay.
So,
Yes, all right. The thing I'm just going to tell Nikita I did not like about this 0.34 is that I want a negative z-score. All right, the z-score is, I'm sorry?
-1.
-1? Okay, then make it easy on us. Great. And we can see that because the mean is 1,200. This is 50 below the mean. Z-score of -1. And what's the z-score up here?
2.
2. All right, math is easy as well. Fantastic. Now, what is the area under the curve? What sort of information do we have based on the chart?
0.3413
0.34. What do you mean? What is that?
for -1. So below,
between the 34th percentile.
yeah. For 1151.
Okay, so where is that? That 0.31. Where on the
Left
chart?
side. Left side.
This side?
No, on the green one.
This
Yeah.
side?
Mhm.
Right, and this side?
It's 0.47.
Okay, all right. I was just checking. So what we get for the 0.34 is just this chunk here.
Yes.
All right. Yes, we're rocking and rolling. All we need to know now is this chunk here.
0.47.
0.47. 0.47 is this chunk here. And remember, we're looking for the total chunk.
82%.
82%. 82%. Sounds right to me. Sanjay? Brandon? Good? Does this make sense? Alright, so this is all I want you to take away from stats in this class. And the more you can get a good handle on that, the more you'll just be ready to go for 601. And arguably, I would also say just based on what we learned tonight, there are some business takeaways you can use as far as statistics. You can use the mean, median, and mode discussion that we went through, interpret how you would read certain data. And when you get thrown some of these types of problems where you're asked to find percentiles or percent chances, you have a good start at how you could answer those questions. So I'll stick around if anybody wants to ask another question. We can go through another example of that, or if there's any questions on the homework or the quizzes from previous classes. And Brandon, did you get the memo of what we're doing with the quizzes?
No. Said you let us redo the first two?
The first three, actually.
Okay.
Yes. So I reset the first three for you. If you need to try them again, and I'll reset them again because you didn't get fair warning, that my recommendation was you look through those, think about how to work them through, but at the very least, just copy down the answers so that you can get full credit on that and hopefully understand those. Yeah, that's all. So just take them again, and if you don't get them all right, then I'll reset them for you.
Okay.
All right. Look forward to seeing y'all next week.